Okay. I'm going to start first, since this was a component of Lab 1, and I commented to a lot of you guys on your figure formatting, that in future lab worksheets, Lab 2 and on, I'd like to see some pretty nice figures and take some time of thinking about how you represent your data. This is a key part of developing as a scientist and engineer, but to point out some of the examples, I always have fun with the bad figure examples in Lab 1, that these are some that I liked that people made with their own Ohm's law data with these very beautiful cyan star data points, no axes labels, hard to discern colors, especially like pointing out, I'll admit that I do this as well, sometimes not considering green and red for the colorblind people and stuff, and having some of the default formats in Origin. Last year, someone put the stonks meme as their bad figure, which always makes me laugh. So I thought I would throw that in here as well. And then this was an example from literature that someone included, one group included, which having an inset, no labels, not really clear what the point of this inset is with two data points. So clearly these are some bad figures, but I'd like to give you guys some pointers for future lab worksheets and things to consider, not just for the worksheets, but in future labs as well, because all of this is important in junior and senior lab reports, when you're doing your senior project, when you're working as a scientist or engineer in industry or in academia in the future as well, if that's the way you go. That's specifically for this lab, I want to point out that Origin default plots are the worst. Many of you guys included the entire legend that they spit out. And the question is it important to include like Pearson's R or these figures of merit for the goodness of fit here? If you're not using them, then why present them? Or it spits out all of the digits based on the fit. So that many of those digits have no significant meaning based on the accuracy or the confidence that Origin spits out. So just because Origin spits it out doesn't mean to include it. I'd also like to point out the difference between using discrete data points versus continuous lines. That when you're collecting data like the Ohm's law plot that you included, if you use solid lines like this, I can't tell, are there actual data points in between here? So usually lines are used to represent fits, while discrete data points will indicate the discreteness of your data. But there's an interplay between, like, if you're collecting at a very fast rate, and if all of your points run together then, and the data is continuous based on the scale you're representing it, then you might want to use a solid line. So thinking about the purpose of the data there. Some other things are the range should make sense. There was just recently a question that in Origin you can edit, for some reason it defaults to have white space on either side, but that's wasted space many times, especially if there's a large range. So you can like double click on the axis and adjust what the range is. Axes should always have units, and if it's a unitless quantity, you should indicate that with AU, arbitrary units, or that it's unitless. And then in the literature, you see that it's very rare that you'll see a title for a figure. So usually getting in the practice of writing captions and writing descriptive captions is good practice as well. And last point I wanted to include is think about the purpose of grid lines as well. Many, like Excel, always defaults to just having horizontal grid lines, but there's not really a reason behind it. Grid lines should be used if you're trying to make comparisons. Maybe if you want to clearly indicate that it's on a log scale, if it's data that's normally linear. So if the grid lines aren't serving a purpose, there's no reason to include them. So these are some things to start to think about. Also, like here, Origin always has like sheet 1, a voltage or something like that. That means nothing to the reader, myself, or if you're sharing this with someone. So I'd like you guys to start thinking about the purpose of what's on the plots and don't just use the default. And even with MATLAB, I've changed some of the figure settings in the scripts that I release. So it's very clear to me if you took the time to edit the figure settings, like many of them won't have axes labels, or I'll use some weird colors or markers. So that's a flag for me to know that like you didn't take time to think about the figure. So going forward, take that time. Are there any questions about that? Comments about when you're making plots? Okay. So after commenting on the figures, let's move on to the actual content of the lecture today, this is related to lab 3. So we're a little bit ahead of the lab schedule. But some of the concepts we'll talk about today even show up in lab 2 a little bit. We're going to be using the Fourier transform in this lecture. So here, lab 3, the next 3 lectures, today's lecture and the next 2 lectures are focused on understanding filters, what their purpose is, what their response is in time and frequency, and how we can mathematically describe that response with the mathematical concept of convolution. So filters are commonly used to remove unwanted information when you're collecting data. So we would call that noise. Electric components that we can incorporate in our circuits to then just get the desired information out, or the signal as well. So big picture overview, these are all the concepts that we'll cover today in the next 2 lectures. What I'm hoping to get through today is on the left-hand side here, introduction to the filters, talking about some noise, and focusing on some of the math is what we'll be talking about today. Convolution, that's important to understand how we quantify and characterize filters with the instrument response function or frequency response function. So this is what we'll be hopefully covering today. And then the next 2 weeks, we'll be getting into details of different types of filters based on which frequency components that you want to remove. So low pass, high pass, band pass filters, and also other filters that don't fall in those 3 classes. So these filters will be covered in lab 3, and we'll get into the details of those in the next 2 weeks. So again, goals for this lecture, what's the purpose of the filters? We're usually removing noise, so a comment on Gaussian noise, white noise, and focusing on how we quantify a filter's response with those. So that's what we're going over today. Okay, so starting out simple, what is a filter? And we're going to define this as a way to change your signal to remove some parts of your signal while keeping others. And I'm going to define this in terms of frequency components. So there's different purposes of this. You might want to separate signals. So this is where if you had signal and noise, so that would be a nice example. So you have a desired signal and you want to remove it from some contamination. With noise or some other interference. So environmental noise. This can also be used to restore a signal. So you might want to remove a distortion. So you'll often see this if you're doing like audio or with images. If you have old audio or old images that you want to remove some noise based on how that was collected. So We're really going to be focusing on electronic filters for this class, since you guys are working with electronics. And these are going to be analog filters for lab 3. So analog meaning that this is going to be hardware based. You're going to be using circuit components to act as the filters, as opposed to digital filters, which we'll get to in lab 4, where you're going to be using signal processing, where you're going to be doing it on the computer after you collect the data there. Also, I mentioned electronic filters because there's other filters, like we talked with images, audio, and in physics, you'll also run into optical filters as well, which I'll comment on that in a little bit. So what you're going to be mostly working on in lab 3 is filtering out some noise. And we're going to have entire lectures devoted to noise later in the semester. But since this will come up in lab 3, I do want to comment on the one type of noise that you'll be using there, which is the same one that maybe some of you guys were able to look at in lab 2. Did any of you guys get to look at the noise section in lab 2? And do you remember what type of noise you were using? I think you're using it from the IFG source. Okay, no one got to that part yet, maybe. So tomorrow, I guess you'll get to it, where you'll be using white Gaussian noise. And so you take a look at the frequency spectrum of white Gaussian noise in lab 2. You're going to be using it in lab 3 to see how your filters are working. And the reason this is called white Gaussian noise and how we're going to define it is that it has a uniform power density as a function of frequency. So if you remember, we talked about like a power spectrum where the frequency was squared. So based on this definition, what we're going to have here is if we plot frequency in hertz, and if we look at the amplitude, the absolute value of the amplitude squared here, what you should see is a straight line. So this would be a plot of the definition that I wrote out here. But with this terminology of white Gaussian noise, some more descriptors to remember what this type of noise is. The white portion of it comes from an analogy with light. So white light has all frequencies. Same way with white Gaussian noise, it has all frequencies based on this plot too, equal components. The Gaussian portion comes from if you plot this noise in the time domain. And if you bin all of if you look at the distribution of the values, it'll form a Gaussian. Or a normal distribution. So if I plotted our signal versus time here, and if we just plotted some Gaussian noise, I'm just sketching this out. This has all frequency components here in the frequency domain. If we summed or if we binned all of these over time, what we would get if we have a histogram, so we'd have occurrence on the x-axis here, and again, we would have signal. What we would get, if I can draw sideways well, is a normal or a Gaussian distribution. So just a comment on white noise, that's what you'll be filtering out in lab 3. Uniform overall frequencies, normal distribution in the time domain here. So that's just an aside of what you'll be filtering out. But as a broad introduction of the filters that you'll be exploring and the different types of filters that you, when you would select to use those filters, it's going to depend on what frequencies you want to keep and what you want to remove. That's how you would select which one. And the filters we're going to go over are low pass filter, which we'll abbreviate LPF. And the key thing is if you read this, you have low and you have pass. So that means you're going to keep low frequencies. Which means you're letting them pass through the filter. And then you're going to filter or reject the high frequencies. So then the opposite of that will be a high pass filter, which we'll write HPF. So that's the opposite. We're going to keep the high frequencies. And we're going to filter out low frequencies. And then finally, band pass filters, which I guess are normally written as one word. So that means it's going to be more selective. It's going to keep a band of frequencies. And then reject higher and lower frequencies outside of that band. So electronically, these are then different circuits. So the low pass and high pass filters are going to be RC circuits, while the band pass filter is going to be an RLC circuit. So we'll go over these next week, and before starting lab 3 next week, I'll also remind you guys you should look at the old Phys 122, the intro labs where you guys worked with RC and RLC circuits. That would be a good thing to review and check on. So these are the types of filters we'll be going over. I also want to note that this is the terminology for electronic filters, and depending on what field you're in, you might hear different terminology for filters that differ than what's used in electronics. So like I work with optics, and there's optical filters to remove certain wavelengths. So instead of filtering out, that's typically viewed as in terms of wavelength with light. So like, for example, I'm using a laser in my lab that we use 561 nanometer light. That would be a green laser. And then we're looking at redder emission, let's say something around like greater than 600 nanometers. So when I'm doing my experiments, I want to filter out this laser light, and I only want to be looking at this spectrum of emission in my sample. So I use a filter where on this axis with this dashed line. This is going to be the percent transmission of the light there. So I keep longer wavelengths and I reject shorter wavelengths here. So 100% transmission of this red light, while 0% transmission of the green laser light. So this is called a long pass filter. So here, this is based on wavelength. These are longer wavelengths. So it's called a long pass filter. So just be aware that different filters, different fields use different terminology there, as opposed to what we'll be talking about in electronics. But usually the names are still very clear on what they mean. We also use bandpass filters in optics where it keeps a band of wavelengths there with that terminology as well. So any questions so far with the noise, with the different types of filters? Just that brief introduction. Okay, so we'll move on. Okay, so we want to describe with those different types of filters, that's verbally what they do, but we want to quantify their performance. So let's say we have a given noisy signal here versus time, and then we introduce some filter or some instrument here, and then we get an output here. So where that noise is rejected. So this is going to be our output versus time. This is going to be our signal versus time, and this is our filter. So we want, our question is, how does this filter perform quantitatively? What frequencies does it cut off? And also it can't, most filters, they can't act instantaneously. There's going to be some time dependence in their response as well. So what is that time response? Which then has a relation to the frequency response. So that's important to understand, to know what we're able to remove from our signal using our filter to get our output here. So what this is defined as, how a filter responds over different times, is called the instrument response function. Or what we call IRF is going to be the abbreviation for that. So this is how we characterize a filter or instrument response in the time domain. And another way of wording this is, how is our signal modified? How is the shape of the signal modified by the filter? So that's our goal here, is to understand and what we're going to be covering over the next several lectures, is for the low pass filter, for a high pass filter, for a band pass filter, given specific electronic components, how does that respond over time in the time domain? And how would that change our signal, and how can we quantify that? So to be able to quantify that, we have to have an understanding of a mathematical concept. So we're going to be going over convolution, is a way that we can quantify that instrument response function. So let's cover this, go over, have a mathematical aside here to go over what convolution is, and then we'll apply that mathematical concept to then define what the instrument response function is and what the response of our filter is in the time domain. So convolution is, we're going to write out the definition here first, and then we'll write it mathematically. It's an integral expressing the amount of overlap between two functions over time. So our first function, we're going to define as capital F sub 1. And we're going to shift that against the second function. Which we'll just call simply F2. And we're shifting it against an arbitrary time. Which we'll define as T prime here. So this integral, what it expresses, what it explains is how the shape of one function is modified by another function. And given, and this depends on the order. So we're going to say how the shape of F1 is modified by F2. So mathematically, if we want to express this definition, how we're going to write this is the convolution, capital C, over a given time is going to be the integral over all space of F1 with this arbitrary T prime times F2 shifted by that arbitrary time. And we're integrating it all over the space of this arbitrary time. And how this is typically written in the notation for convolution is the asterisk symbol here. So the asterisk here means the symbol for the convolution integral over here. T prime here is going to be a dummy variable. You can see that it's not in the final result. The final result, the convolution here is all in real time, the T. And this is just indicating the shift. And an important thing to note here is that in this equation is that it's T minus T prime, and it is not T plus T prime. This is important, that you would get a result, different result if you added them. So the subtraction there is something to note. So I'm going to try to do a visual representation of this. I apologize in advance for probably my bad sketching skills on this little tablet I'm using. But let's consider, we're going to consider two functions here. We're going to start out with a Gaussian. And we're going to say on the y-axis, it has an amplitude of 1. And to keep it simple, it just spans from a value of 1 to 3 here. It's all contained between on the x-axis, these values of 1, 2. So this is going to be our f2, is going to be a Gaussian function. And we want to convolve this with a step function that has an amplitude of 1. At a certain value, it shifts up. And we're going to have our x-axis just be simply time, and then we'll just have amplitude for our y-axis here. So what I want to do, this is going to be our f1. This is going to be a step. So we can write this out in the integral form that I showed on the previous slide. We're going to say we're going to convolve a step function with a Gaussian function, which is going to be the integral over all space, or all time, that dummy variable time. Yeah. Here, so that's how we'll write it out. So our resulting plot here is going to be, the x-axis is going to be in time, and then the y-axis is going to be our convolution value here, and it's going to have 3 different regions. So the first region is going to be where there's no overlap between the Gaussian and the step function. So we're going to look at t prime here. We're going to have our amplitude of 1 here. And our step function, this f1, stays fixed in this t prime variable here. So there's our step function. Our Gaussian function, if it's in an area, the first thing that happens is because of this subtraction here, the Gaussian function is flipped. But since we have a symmetric Gaussian, that's not very apparent. So we're going to flip the Gaussian and we'll shift it by t prime. And in this region 1 here, there's no overlap. So with the no overlap here in the integral, what this means is that it's going to be equal to 0. This equals 0. So for the first portion of our convolution, there's a section where it just equals 0. That's the first region here. So if there's no overlap between the two, that integral is equal to 0. The second region is when we're going to shift that Gaussian and there's going to be partial overlap between the two. So if this is our step function, at some point that Gaussian, as we're shifting it over in t prime in this space, it'll start to overlap and our integral will start to have a value. So then at that value of t prime, or at that value of time, we'll start to see an increase here. And as it shifts over more and more, it's going to keep increasing and increasing. So there's values in between here. This is going to keep increasing as it shifts over. And then the last region we have, well, here in this region 2, the convolution is going to be proportional to the amount of overlap between the two, we're going to see an increase in C in the convolution. And then the final region, region 3, is when there's complete overlap between the two. So if I sketch this out, here's our step function. That's when the Gaussian is completely under here. And as you shift it more and more over, it's going to be a constant again. So this is what our convolution plot will end up looking like. The final plot based on these 3 regions. So you could see that our sharp step here, our sharp step function has been broadened out. That the Gaussian has kind of, has been blurred out. And this will be dependent on the width of the Gaussian. So if you had a thinner Gaussian, this would occur much sharper. It'd be closer to the step function. While if you had a wider Gaussian, that slope would decrease there. So this is just an example of a step function and a Gaussian. And while here we've been integrating from negative infinity to the infinity, you could see that if we kept going to negative infinity, that would be 0. If we went to positive infinity, that would be still that same constant. So you could define the limits of your integral there based on like what the range, what the width of that Gaussian is and where the center of your step function is here, if we define this as 1. So that's a slowly sketched out convolution of a Gaussian and a step function. I've included these animations here that are stolen from Wikipedia, but are very nice and much clearer compared to my hand drawing, where we have 2 step functions shifting past one another here, where you can see it starts to, the blue is your first function, your red is F2. This black line represents your convolution. And the yellow is the area under that integral in between there. So you can see this triangle shape for 2 step functions. And then you can see with the step function and the exponential, the convolution between those two, which this type of convolution will be important when we get into discussions next week as well. And also in lab 3, you'll be working with MATLAB to make these kind of plots yourself as well. So to wrap up the convolution, the mathematical side here, I do want to share some of the mathematical properties. So I do want to correct something that I said earlier, that I incorrectly said that the order matters, and it doesn't, that there's a commutative property of convolution, that if you convolve F1 with F2, that's going to be the equivalent of F2 convolved with F1. So the order does not matter. So I said that incorrectly earlier. There's also the distributive property. If you convolve F1 with the sum of 2 functions, that's going to be equivalent to doing those separately. And the associative property. That the order that you do these does not matter. So any questions about convolution at all? Okay, So hopefully in the last bit of lecture, so there's enough time for your quiz, let's go back, let's get through the last part of this. Like after all that stuff about convolution, why do we care about this? Well, we need convolution to be able to describe the instrument response function. To understand and quantify how our filter modifies our input signal to get our output function here. So the instrument response function can be determined using a convolution in the time domain specifically. So for our given signal input, here S of t, and our output signal O of t here, we can write this as O of t. Our output is going to be a convolution of our input signal with the instrument response function in time. So IRF t minus t prime all over dt prime. So we can write our output signal is our input signal convolved with the instrument response function in time here. So convolution is a mathematical tool that you'll use that to understand how your signal is modified in the time domain. We can also do this in the frequency domain as well, and that's called the frequency response function. Which we'll abbreviate as capital phi here with our omega. I'll write a little subscript IRF. So this is the IRF in the frequency domain. And this is simply going to be the Fourier transform. So getting back to lab 2, in your current work, this is where Fourier transforms are coming into play. That you can characterize this. In the time domain, take the Fourier transform, get your frequency response function, or vice versa, characterize it in the frequency domain and take the inverse Fourier transform to get your instrument response function. So that's mathematically how we're defining this, these equations for the IRF based on convolution and Fourier transforms. But how would we actually characterize this in the lab? So how you would determine the instrument response function or the time response of your filter is you would want to send an ultra short signal. So last lecture, we talked about a bunch of different functions. What's a good example, or what did we discuss that's an ultra short signal that might be ideal for determining the instrument response function? Any ideas?
The delta function?
Yeah. So Jack says a delta function. Would be the most ideal. So we can write this out based on our definition of the instrument response function that we could take the convolution of a delta function with our instrument response function. And the output should then be the instrument response function itself, based on the property that our delta function is 0 everywhere, except when t is equal to t prime here. So based on that property, our output, if we send a delta function in, is going to be our instrument response function here. So to determine your instrument response function in the lab, you want to send a delta function in. You clearly, a delta function, if you guys remember, is how we define it theoretically is it's 0 everywhere except at one value, and the area under that curve is infinity, or exactly 1. It's exactly 1. So we can't ideally produce a delta function in the lab. So in the lab, some ideals that are a very short top hat or square wave pulse. And if that square wave pulse is shorter than what your instrument response function is in the time domain, then it can be approximated as a delta function. Or an alternative is to send a step function in. So those are the two options there, but understand that like with the square wave pulse, it's going to scale. Your IRF is going to scale with the length of that pulse. And lab 3 will walk you through that. So I think I covered everything with maybe a minute or two to spare. So do you guys have any questions about the instrument response function, frequency response function? And I'll do a brief overview of this next week as well. Any questions?
Is O of T is that supposed to stand for the output?
Yeah, output.
Got it.
Any other questions?